Thank you. Thank you, Ben. What's on the screen at the moment is a little side project of mine, which is a visualization of MQTT packets being sent between clients and servers. I'm planning to put it onto an open source repository next few months so that people can contribute and take advantage of it as well if they want. It happens to be VR enabled, so it works in VR, it works on my Oculus Rift, which I recently got, so it's cool. Okay, let's get on to the presentation. So I'm going to talk about MQTT. Now we're on. MQTT is probably a protocol that some of you are familiar with. Well, let me ask that question. How many are familiar with MQTT in the room? Okay, that's about a third, I think. Raise their hands, so that's good. It's a protocol to enable devices to easily connect to other machines, whether that's a cloud server or a local gateway, sending and receiving events, getting that data from your endpoint, your device endpoint, into your cloud application. My name is Craggs, and I work for IBM on the IBM Watson IoT platform, one of the screens of which is shown there. And I also work, or mainly work, on Eclipse Paho as the project lead and maintainer of several of the components. I've worked with MQTT since the early 2000s. Worked with one of the inventors of MQTT called Andy Sanford Clark, who also knows very well the other inventor of MQTT called Arlen Nippler, who was the CEO of one of the companies that used MQTT first to solve a particular problem. I've written a broker called RSMB. I also worked for IBM brokers, and now I also have some contribution to the Eclipse Mosquito project. And in Paho, I'm a maintainer for the C client, the embedded C client for MQTT, also the embedded MQTT-SN C client, and the MQTT test material, which is mainly written in Python. So this is the agenda that I'm going to go through today. MQTT 3.1.1 was standardized fairly recently. So one question you might be asking is, why do we need a new version of MQTT quite so soon? Then I'm going to go through where we are with MQTT version 5 and run through all the changes and advantages of MQTT version 5 over version 3. And then some of the implementations that are available already. One thing that I've noticed from presenting this before is that when I repeatedly try to say MQTT 3.1.1, that's a bit of a mouthful. So I'm going to use version 3 to refer to MQTT 3.1.1 and 3.1, which are very, very similar. So version 5 versus version 3, that's much easier for me to say. Okay, do we need a new version of MQTT? Or why do we need a new version? I'm going to start from a historical perspective. This is a page from the Doomsday Book, which was written in the 10th century as a means for the French invaders to work out how many taxes they could extract from the newly conquered English. And this page from the Doomsday Book is actually referring to the village that I live in today. So this was from the 10th century, and the village still exists today. This book was put together over a period of a year by 3 or 4 commissioners that were sent around to all of the regions of the UK. It took a year to put together, and by the time it was put together, to determine how much tax could be extracted, then you might say it's going to be out of date. This is a polling problem, the sort of polling problem that MQTT was designed to solve. So come to the 20th century, and this is the original problem that MQTT was invented for. This was oil pipelines running through Alaska or Nevada, thousands of miles in remote places, and they wanted to be able to monitor the oil pressure across those thousands of miles to make sure that there weren't any oil leaks. The original solution had devices, pressure sensors along the whole range of the pipeline, and the central server would poll each of these devices, get the information back about the oil pressure, then work out where the oil leaks were. Because the central servers, and remember this is 20 years ago, so they weren't as powerful as they are now, were monitoring and polling all of these devices, then this was overloading the central servers because they were spending all of their time polling and not doing anything else. So MQTT was designed to address that problem. And the way it was addressed was to put concentrators at remote points along the pipeline. Each of those concentrators used an MQTT client to communicate to the server, the central cloud server. The concentrators were attached to the pressure sensors. All of the interaction with sensors was dealt with by the concentrators. When the information changed about the oil pressure, then the information was sent over MQTT, over the satellite links, which were both expensive and unreliable at that point. So they needed to minimize the amount of bandwidth that was sent over those satellite links. And MQTT accomplished all of those things. One of the aspects of MQTT that you might think isn't necessarily conducive to that is the fact that it uses TCP/IP. But when they were thinking about how to solve this problem, they realized they wanted to be able to make the communications reliable, even though it needed to be lightweight. And if they were going to make it reliable, they needed to have error correction and that sort of features, all of which are in TCP/IP. So rather than reinventing the wheel, they used MQTT relies on TCP to provide that sort of reliability, error correction, etc. So yes, TCP stacks are, compared to UDP, quite significant in size, but those characteristics were needed for the MQTT purposes. So that was the first solution. And since then, MQTT has gone through several iterations. It was published just right from the start as an open specification by IBM. So there were no restrictions on people implementing MQTT. One of the reasons for this, even at that early stage, was that IBM realized that if MQTT was going to be a success, it needed to be implemented by hardware vendors of all sorts. We couldn't provide solutions for all of that hardware. It needed to be open to allow other people to implement it for their particular devices. So the specification was open from the start, the late 1990s. MQTT first appeared in IBM products in around 2002, and in 2013 the MQTT standardization process was started. That concluded in 2014 with the standard of MQTT 3.1.1. In parallel with that, we've got some MQTT-SN efforts, which I'm not going to talk to in detail today. I'm going to leave that to another talk for another time. But MQTT-SN is a similar specification produced by IBM, which brings MQTT-like protocol to non-TCP networks like UDP and CP. So 2014, that was when the first MQTT standardization was complete. These are some of the goals from the very first draft of MQTT. We wanted to keep it simple. It needed to be have low resource requirements, but still be reliable. And in the 1990s, large numbers of clients were, well, the first specification was talking about 50 clients to a broker, not 10,000. And today, people talk about hundreds of thousands, or maybe millions or billions of devices. And right from the start, it was an open specification to encourage implementation. Also, industry agnostic. One reason MQTT has been called a transport rather than a protocol, because the payload is not specified. There's no particular details. You can write any sort of data into that payload to be transported by MQTT. The idea was to separate the implementation of the information exchange between devices and gateways from the means of getting that information from one place to another. So unlike a SCADA protocol, for instance, which details all of the payloads, then MQTT was meant to be agnostic of industry to allow different implementation, different communication mechanisms to be implemented over MQTT. If you want to ask me questions afterwards, I'm going to be around all day to answer any questions that you have. This is just an indication of the popularity of MQTT. The top two sections on this graph are Eclipse Paho and Eclipse Mosquito, which are client implementations of MQTT and a server implementation of MQTT. And those are the top two websites in terms of traffic in Eclipse IoT. And this is a chart from the most recent Eclipse IoT developer survey, which has MQTT as one of the top protocols used in IoT implementations. These are very rough guides to the popularity because there are all sorts of reasons why it's not perfect, but it's just an indication of the popularity. So, when we standardized MQTT 3.1.1, the primary goal was to reach a standard as soon as possible. To do that, we wanted as few changes from the existing 3.1 specification as possible, and to allow existing implementations to work virtually unchanged. So the specification charter for the technical committee at OASIS allowed us to change very little. Only the connect bucket was really available for us to change. That meant that some of the common issues with MQTT version 3 were not being able to be addressed in that first standardization effort. There was a lack of error reporting. Some of the published packets weren't able to produce negative acknowledgements, which meant that the server, if they found an error, could only terminate the TCP connection. Then a client might restart its communication efforts and produce the same errors all over again, and then you get into a nasty loop. So we wanted to be able to fix that. There's no properties, no metadata on messages. I thought this was not necessarily a big problem because the payload in MQTT was not defined. You could add those properties into the payload, but having separate fields for that metadata it seems to be useful for many applications. State is required to be held cross sessions for certain aspects of MQTT, which makes it more difficult for cloud implementations, and load balancing wasn't really a feature that we enabled. So MQTT version 5 was created as a standardization effort soon afterwards to solve these issues, these remaining issues with version 3 of MQTT. I'll just pause here to say something about why we're calling it MQTT version 5. The previous version is version 3.1.1, so it might be natural to call it version 4. Well, in the connect packet, we only have 1 byte of version number, which means that we have whole numbers as version numbers. And version 3.1 used 3 in the connect packet. Version 3.1.1 used 4 in the connect packet, which is quite confusing when you come into looking at the details of implementations. So we decided to make the numbers match, and that means we have to use 5 in the connect packet. So this is version 5 because we're using 5 in the connect packet. It's 5.0 because OASIS insists on having a dot and a version number, subversion number. So that's the reason it's 5.0. If we do the next version of MQTT, it'll be 6 in the client packet, and it'll be called 6.0 by OASIS. So the first thing that we did in the technical committee for version 5 was to take those issues with version 3 and turn them into categories that we could put ideas for new improvements and rectifications into the charter for version 5, and work on those as our guidelines for producing the new version. Those are the areas which roughly correspond to those issues that I presented earlier. So we turned that into a charter for the version 5 technical committee, and that, on the right-hand side, those are the main members of that committee. As you can see, or you might be able to read from there, the primary constituents from an industrial point of view, a company point of view, are IBM and Microsoft. So Microsoft weren't present in the standardization for version 3. It was a welcome addition to have them on board because it meant there was an alternative viewpoint to IBM. I think it also increased the influence and the believability of this committee to have Microsoft on board as well. So that was very useful. That's not quite true now. We're more advanced. That'll be our here point. So we're almost right at the end of this timeline. We only have a few bits of red tape to clear up, and hopefully by the end of this year, the standardization process will be complete. We've gone through 2 public reviews. I've had comments from that, so we're almost at the end. That was just a copy of the first public review draft, of which we're on number 2 now. So I'm going to quickly run through all the changes, the major changes between version 5 and version 3. They're roughly in these categories, the categories that I mentioned before, big ideas. Scalability in large-scale systems, improved error reporting, extensible metadata, and resource-constrained clients and performance. There were already 14 packet types in MQTT version 3. We've only introduced 1 new packet type for version 5. That's the auth packet to allow extended security exchanges, challenge response security. Version 5 doesn't specify how you should use this packet, similar to the publish payload. The actual details of the exchange are not specified by MQTT, so you can use it to implement challenge response in whatever way you like. Improved error reporting. The first aspect of this is that there are reason codes which are predefined on every response packet. So this is an extract from the specification. Reason codes take 1 byte. The values from 0 to 127 indicate that there's a successful response. 120 and above indicating an error. In quality service 2 exchanges, there are 4 packets that flow back and forth. In version 3, if something went wrong in the middle of this exchange, the only option that the sender had, or the receiver, was to either continue the exchange to the end and pretend it all worked, or terminate the TCP connection. And then the worst case is that the sender restarts that communication, ends up recreating the error, and you end up in a loop. In version 5, if there's an error partway through that exchange, you can signal that to the other end of the link, and then that stops. So that's much more efficient. And because you have a reason code, it means that the person that the implementation at the other end of the link can have an idea of what the best action is to take. If the reason code says, this is a permanent error, don't try this again, then you might report that to the sysadmin to go away and figure out what's gone wrong. If it's a temporary error, then it can be retried safely. Every packet now has a set of properties which are available, except pings and ping responses. We did discuss whether we should add them to pings as well, but we decided against it because we thought this could end up creating a mechanism for people to build their own protocol entirely out of pings. So we avoided that. There are user properties, so you can use those for your own purposes, as well as a set of predefined properties which have been very useful to implement some of the new features in version 5. This was a particular bugbear of mine in version 3 of the protocol. If you wanted to start off with a clean slate of a session, clean up any previous state that's been left around, but continue with reliability over network breaks, that's using publish quality of service 2. You had to go through the exchange at the top to get this to work in version 3. You have to have 4 packets. Connect clean session true, which will clean up the session at both the beginning and end. And then disconnect. And then connect clean session false. With version 5, you can do this in 1 packet. Connect clean start true with an expiry interval of infinity. You can set it to other values. That expiry interval specifies how long the session state should be retained by the server after the connection has terminated. In version 3, the only way that the server had of telling the client something had gone wrong was to terminate the TCP connection, because it wasn't allowed to send the disconnect to the client. In version 5, now the server can send this disconnect, along with reason codes and properties on the disconnect to describe exactly what's going on, so that the client application can be much more efficient in its handling of those errors. We have limited support for request response type topologies, so MQTT uses pub/sub, uses topics to subscribe to, and you publish to those topics. You don't know who's subscribed, how many people are going to receive it. Request response is a bit more like a queue. The way that we implement that is that we have a response topic property which the sender can specify. The receiver then sends a response to that reply topic, and there's also a correlation ID property which can be used to match responses to replies, responses to requests. We do have a payload format indicator property, but there are just 2 values that are used. Either binary byte arrays, which is similar to version 3, or UTF-8 strings. We did have quite a long discussion in TC as to whether we should have, how many packet types, or payload types we should have, whether we should use minor types, or some other previous definition. But agreement was difficult to come by, so we ended up with the lowest common denominator, and we didn't want to be in the business of managing a list of payload types. So whether we will gradually increase this list, I'm not sure. I think we'll get user feedback on this and see whether expanding this list will be useful. For load balancing, we now have shared subscriptions as part of the specification. So this turns a topic almost into a queue. It means that If you use this topic format at the bottom, so $share, the filter part of the topic name is the usual topic filter. The share name is a group, a subscription group. So every subscriber that uses this syntax with the same, as part of the same group, will share the subscription. So that rather than all of the subscribers in that group receiving the message, only one of the subscribers in that group will receive it. Which means that if you want to increase the throughput for a particular topic, you can allocate more subscribers to that group, as many as you need. And if you want more than one group for the same topic, then you can do that as well. The specification doesn't say how that distribution should work, so it leaves it up to the server to decide how it should allocate the messages between the subscribers in that group, which follows one of the principles of MQTT of not constraining implementations more than it needs to. We have no local subscriptions, which any of you familiar with JMS should be known to. So that one of the first experiments people often do with MQTT is to write a chat application. Then one of the irritations then is that you get the messages back that you publish. The no local option allows you to decide whether you want to get messages sent by the publisher back to the publisher or not. We also have retained message control in version 3. There was only one option, which was version 0. All retained messages at the time of the subscription will be sent back to the subscriber. Now we have the option of receiving retained messages only for new subscriptions or not at all, which is especially useful if you're going to use MQTT to bridge or connect one MQTT server to another. It's also useful for applications. We have topic aliases, which is an idea taken from MQTT-SN, which is the ability to reduce the size of published packets when you're using a long topic name. After you've used it once, you can replace the topic name with a number, a 2-byte integer. And to enable some cloud applications and help small client applications like those running on Arduinos, for instance, we have the ability to advertise the capabilities of senders of both brokers and clients. So from the client side, we can say what's the maximum packet size that we can accept, the client can accept, and the maximum number of concurrent QS12 messages that a particular client can handle. These are important because both of these require storage. So if you're working on a very small constrained device, you want to be able to specify these limitations. It's no good sending a 100 megabyte message to an client implementation on a 16K Arduino, because it's just not going to be able to handle it. Then it's up to the server to decide what to do with that message if it accidentally is sent to a client application that can't handle it. And that's an administrative task. You might put a log message out, but also send a message to a sysadmin to say, this situation has occurred. It means that it can be handled much better. Likewise, there are capabilities that servers can advertise. Whether retained messages are available, which quantities of services are supported by that server, maximum packet size again, and the number of concurrent queues, 1 or 2 messages also. Again, this means that clients and servers can tailor their behavior to the abilities of the other end that they're communicating with. We also have subscription IDs. So MQTT allows you to subscribe to wildcard topics. Occasionally you might do this a couple of times, so you could say subscribe to topic A and to a wildcard topic hash, which subscribes to everything. Then, when a message comes to you, you might get 2 messages, or might get 1 message, depending on the implementation. And that message might have matched both of those subscriptions, and you didn't know which. In some cases, it's useful to know which subscription matched. For instance, in client libraries, if you want to have per subscription message handlers. So subscription IDs are properties that are attached to the message which tell you, as an application developer, which subscription is matched. Those concurrent QoS1 and 2 messages properties that I talked about in the couple of slides back, those enable a modicum of flow control. Because if the client says, or the server says, I can only handle 2 outstanding quality of service 1 or 2 messages at a time, then the sender has to buffer and not overload the receiver. So this provides a form of flow control. It doesn't affect QoS0. We did think about ways of helping QoS0 flow control, but that was too difficult to add with the current state of MQTT, and I think that there are other ways of addressing it. So those are all of the features that we've added to MQTT version 5. We hope to have the standards finished. It's in a state where no substantial changes are going to be made from now on. So if you use it as it stands, then you're on safe ground. The only remaining tasks that we have are really red tape to get the final rubber stamp put onto the specification. I don't think that version 3 is deprecated. I think they'll coexist for a long time, version 3 and version 5, because there are different capabilities. Although we have had quite a lot of take-up of version 5 in the last few months, so maybe my prediction will be wrong. Certainly there are lots of version 3 implementations, so I think those are going to be around for a long time. The next task for the standardization effort might be to look at MQTT-SN, which is MQTT for non-TCP networks. And if that happens, then I'm probably going to do that. So if anybody's interested in contributing or helping out with that effort, then let me know. So I released just last week the latest version of the Eclipse Paho C client for MQTT, which contains support for MQTT version 5 and WebSockets. That's the 2 main highlights. And I've written a few blog posts about it, and how I've also improved the command line utilities so that they can easily be used to send and receive MQTT version 5 messages. Paho also has a Java client library, and that's almost at the end of its cycle of development for version 5. I'm working with the developer of that to try and get beta out as soon as possible, or even full release. In Paho, we also have a Python MQTT broker, and I've got a full implementation of version 5 in that. That's just a screen of its startup. It also supports version 3 of MQTT, TLS connections and WebSockets, and we use this for the continuous integration testing of the Paho version 5 clients. It's available from the URL at the bottom, so you can, it's all open source obviously, so you can use it. And I've also set it up at this URL so that you can try out MQTT version 5 exchanges right away if you need to, or want to. For the other plans, we also, you might know that we have an Eclipse Mosquito as an MQTT server. It was announced that they were planning support for version 5 in August. That hasn't happened yet, so we're working out where that support actually is. So we've got C clients just released with version 5 support, test material broker, the Java client almost done, and I'm halfway through the embedded C client support of MQTT version 5. Some of the implementations other than Eclipse IoT, IBM has recently announced a beta version 5 in their Watson IoT MQTT device platform. HiveMQ have early access version 5 support available. HiveMQ is a company in Germany that provides servers for MQTT. VernMQ have recently announced full version 5 support. Again, another server implementation. And a company called Flesby.com from Eastern Europe also have an online version 5 MQTT broker. So, as I said, from existing MQTT implementers, we already have a substantial number who've shown interest in version 5. So, how much time do I have available? 5 minutes, okay, cool. So, I'll take any questions while just going through a quick demo of implementations that I have. So, if you have any questions, then please do ask them. So this is the Python broker from the Paho testing repository. I just started that. And it's in its default localhost configuration file, which we use for the continuous integration testing. It's got version 5 support, version 3 support, and TLS and WebSockets in a bunch of different configurations to allow all of these tests to work. I've got the Paho command line utilities running in a couple of different windows. So this is the subscriber Paho_C_sub. It's pretty small, but -V5 means use version 5, and if I enter that, I'll actually put the trace protocol option on it, which will show the protocol exchanges. So it shows some build information, and then the fact that we sent a connect packet. Oh, so it's a demo, right? So it's not going to go right. Oh, that's worked. Okay, we've got to connect a comma, subscribe, and then we had some problems. Interesting. Okay, let me go to this other window. This is publisher. Let me just stop it. So the other one was Paho C sub. This is Paho C pub, which is the publisher. And if I've connected successfully, then we should get the message sent from one to the other. Oh. Okay, it's still not working. This is going to work afterwards. I'm going to have to trace protocol exchange, extra option on that. Okay, so that shows how you would use the. Okay, this is subscriber sent to. That shows how you would use the command line utilities to send from one to the other. And we also have the IBM Watson IoT platform IoT service, and I should be able to send messages to that from here using version 5. Okay, just going to start this. So that's connected to the platform. It shows the SSL exchanges that happened, as well as the version 5 packets that were sent and received. And then if I send some message, that was formatted and understand because it's expecting JSON. So I just have a JSON value. And we get I'm going to show you, and I'll just put another one in. And it shows a quick connection using version 5 to the Watson IoT platform. Okay, that's all I have for today. So, do we have any questions? Okay.
Hi. Yeah.
Hi.
Can I ask if we use transmission system like LoRa with very low data latencies, and would the MQTT be able to handle timeouts for very long sequences or rings in LoRa transmissions?
So, I know some companies who use LoRa, but they tend to use MQTT from the LoRa gateway to the cloud rather than over LoRa itself. I think that MQTT-SN might be more useful in a LoRa context than MQTT, but I haven't looked at the details to know. I think one of the options of either MQTT or MQTT-SN would work for LoRa, but it might be MQTT-SN rather than MQTT. Because MQTT relies on TCP, so the underlying transport has to have the characteristics of TCP, has to have error correction, reliability, and sessions, for instance. So it depends what capabilities LoRa has.
Is MQTT-6 something that's already being discussed?
No. I think that we're happy for version 5 to have a long life. And so it's always a balance between putting these capabilities in and making sure that the protocol is still lightweight, because that was one of the main goals of MQTT. So I think we've done a reasonable job of that in version 5, which is one of the reasons why I said I think that version 3 and version 5 will coexist for a long time, because maybe people will be happy with version 3. On the other hand, because of the uptake we've had so far, I might be wrong about that, and version 5 might overtake version 3 very quickly. So, no, version 6 is not, nobody's even talked about that. That's why I said the only other item on the committee's list is really MQTT-SN, non-TCP networks.
Thanks for your presentation, and one question. Is the specification for this version number 5 is already complete, or it can be possible any modifications in next months?
Basically, it's complete. So we have some rubber stamping to do to finalise it. We've been through two public review drafts where we've got comments from people outside of the committee, and we've addressed those. So I think you can safely use it as it stands, and there are going to be no changes from now on. So it's finished, basically. Okay. I think there are no more questions, so we'll stop it there. Thank you.